for flexible energy harvesting and storage devices. I'm Charlotte, Journal Publishing Manager from Wiley, China. First of all, please allow me to give a brief introduction about our journal. EcoMat is a flagship journal published by Wiley in collaboration with the Hong Kong Polytechnic University. It is a gold open access journal, and we aim to publish on a wide variety of topics from different disciplines that focusing on cutting-edge materials for green energy and the environment. The scope of EcoMat is intentionally broad, including energy harvesting and conversion, batteries and supercapacitors, energy systems and networks, fuel cells, thermal, piezo and triple electrics, carbon capture and storage, pollution control, catalysis, etc. The articles can be immediately opened once published with a rapid average publication speed. EcoMat has already published 16 issues online so far since it was launched in 2019, and the article publication charge is waived until the end of this year. Our ambition is to make a mark in material science and its adjacent fields of a high academic impact. Here, I would also like to introduce a bit about our dedicated editorial team. Our editor-in-chief is Professor Zijian Zheng from Hong Kong Poly U, and we have 5 associate editors now who are Professor Song Bingyuan from Northwestern University, Professor Sang Yisuk from UNIST, Professor Qiang Zhang from Tsinghua University, Professor Huijun Zhao from Griffith University, and Professor Ximi He from UCLA. We also have the managing editor, Dr. Luo from Hong Kong Poly U. EcoMat has already been indexed by SCIE, DOAJ, and CES so far, and we just received a first impact factor of 12.213 and first journal citation indicator of 1. On behalf of EcoMat and Wiley, I'd like to say a big thank you to all editors, authors, reviewers, and other contributors. We can't make it without your continuous strong support. Last but not least, we welcome you to follow our social media accounts. Please scan the code here and follow our news on WeChat, LinkedIn, Facebook, and Twitter. And we have a new WeChat group for our researchers who would like to have more communication with us and each other. Also looking forward to your next submissions. Currently, we accept research articles, review articles, and research highlights. Now, I'm excited to hand over to our guest chair, Professor Ximi He, to start today's webinar officially. Please do not be shy to post your questions in the chat box during the meeting. Many thanks.
Thank you, Charlotte. Thank you very much for coming to our webinar today. Good morning, good afternoon, and good evening. So it's my great pleasure to have our 2 excellent speakers to give us share their research with us. So the first talk will be originally we invited Professor Pei Wu, and now Professor Yucong Jiao kindly step in to present equally exciting research from their group. So briefly, I would like to introduce Professor Yucong Jiao from Donghua University. Professor Jiao is currently a professor of College of Chemistry and Chemical Engineering at Donghua University. He received his bachelor degree from Department of Polymer Science and Engineering of Zhejiang University, and his PhD in the Department of Molecular Science at Fudan University. So after working as postdoc fellow at Northwestern University, he joined Donghua University in 2018. His research interests mainly focus on polymer design for advanced batteries, including the hydrogel structure design application on aqueous batteries, molecular interaction regulation for solid-state lithium batteries, and inorganic material self-assembly. So in today's talk, Professor Jiao will share with us about their really exciting recent work on molecular interaction regulation in advanced polymers. So without further ado, I would like to give the platform to Professor Jiao. So please start sharing your screen.
So, can I see my slides?
Yes.
Okay, thank you.
You can start the presentation mode if you can.
Okay. Okay.
All right,
So-
perfect.
Thanks to Professor He for introduce me. Because of the health reasons, Professor Wu cannot give this talk, so I will provide the presentation here. So I'm Yu Songjiao from Donghua University of China. So today my topic is about the constructing and regulating the molecular interactions in polymer gel for advanced batteries. So I will give this talk following the following three parts. So as we know, the lithium batteries, they have already occupied the commercial market for decades, but the safety issue still impede us there for the applications on flexible and variable batteries. And for the aqueous zinc-ion batteries, they use water as a solvent, so they are much safer. So they are much safer and environmental beneath. In addition, they are low cost and have high capacities and many other advantages. So they are more promising for the future variable and flexible batteries. But they have two severe issues need to be conquered before their practical application. So the first one is the dendrite and side reactions. The second one is about the anti-freezing performance. So here in this topic, I want to provide the strategies to regulate the molecular interactions in gel electrolyte to texturing the zinc ion nucleation crystal plane, to regulate the zinc ion solution structure and modulate the hydrogen bonding in the gel electrolyte to inhibit the dendrite effects and enhancing the anti-freezing performance of the zinc ion batteries. Okay, so the first one is about using the gel electrolytes to texturing the zinc deposition crystal plane. So here we employed the weak ionics, as we know, the weak ionics on a large amount of the charged groups, and they can form the electrostatic interactions with zinc ions. Thereby, they can render the higher zinc ion migration rate, uniform interfacial electric field, and reconstructing the zinc ion solution structures. So the strategy here is we use the bacteria cellulose as backbone and polymerize the imidazole-based weak ionic on the bacteria cellulose to form the dial network polymer gel electrolyte. So for the zinc ion solution structure, we know they usually have 6 water molecules around the zinc ions. This molecule will get the electron on the surface of zinc metal and cause side reactions such as HER or some other side reactions. With the electrostatic interactions between the weak ionic and zinc ions, the solution structure can be constructed, and there are only 4 water molecules surround the zinc ions, and which will help to inhibit the side reactions occurred on the zinc metal. Thereby, we use NMR and Raman spectra to confirm that the existence of the electrostatic interaction between the imidazole ring and the sulfate, between the sulfonate and the zinc ions. In addition, we also use the Raman spectra to confirm that the zinc ion solution structure is reconstructed. So as a result, we can see that the electrochemical stability can be enhanced, and the side reactions such as the hydrogen evolution reaction can be inhibited. From the XRD result, we can see that there's no byproduct with the weak ionic gel electrolyte because of the interaction of the electrostatic interactions. More interestingly, we can see that after only 50 cycles, the peak for the 002 crystal plane increased significantly. So for the 002 plane, they have much higher activation energy for zinc dissolution and to resist the corrosion and to help to inhibit the side reactions. So with the help of the ionics, we can find that the 002 plane increased very quickly. And from the SEM image, we can also see that there's well-defined and distinctly layered hexagonal zinc C02 structure. More interestingly, even after six months, we can still find the obvious hexagonal structure. Which means they are very stable and they can resist the corrosion from the air. So we use the TFT to demonstrate that this structure is due to the planar imidazole ring and due to the synergistic effect for the imidazole ring and the sulfonate. The planar imidazole ring can parallel along the zinc 002 plane, and the sulfonate groups can stick to the zinc atom. Thereby, they can guide the zinc ion to grooves to deposit and nucleate on the along the 002 plane, crystal plane, and to accelerate their growth. So as a consequence, we can see that even at the high current density, as high as 7.5 milliamp per square centimeter, they can still cycle stable for more than 400 hours, which have already surpassed most currently reported literatures, especially on the gel electrolyte field. In addition, we checked the full battery performance. We use manganese dioxide as the cathode and find that with the help of the weak ionic gel electrolyte, the battery can own a high ion conductivity, high zinc ion transverse number, and they can provide high stability for over 1,000 cycles and the high current density of 5C. For the flexible battery application, we also assembled the flexible devices and checked the cycling performance. We can see that it can cycle stable and provide a high specific capacity, and they can also power the lights and the various destructive experiments. So in this part, we provide the weak ionics to form the electrostatic interaction with zinc ions to guide zinc ions crystal plane. We also check the anti-freezing performance. So usually, for the aqueous electrolyte, because they use water as solvent, so they are safety, but they are safe, but the freezing point is very high for the aqueous electrolyte. So it's very easy for us to think that we can edit some additives which have much lower freezing point but for the dimethyl, the dimethyl sulfate oxide, they are more special. Their freezing point is higher than water, but after the mixture with water, the hybrid electrolyte can provide a much lower freezing point than water and than dimethyl. So which means that the dimethyl can form a new hydrobonding with water, and this may significantly lower the freezing point. And so we use the FTIR, the Raman spectra, and MR to further demonstrate that the hydrobonding between water molecules is weakened, and a new hydrobonding between dimethyl and water formed. So thereby we check the electrochemical performances and find that the hybrid electrolyte owns the stronger nucleation driving force and the more fine-grained zinc deposition morphology, low corrosion tendency, and rate. And thereby the performance for the cycling performance is also very good, very stable. But when we check the DFT result, we can find that with more water molecular is replaced by the DMSO molecular, and the zinc solvent structure, the radius of the zinc solvent structure increased. And with radius increased, we can see that ionic conductivity gradually decreased. So this means that with this kind of additives, so they can improve the cycling stability. They can inhibit the side reactions, but the ionic conductivity decreased, thereby the rate performance of the battery will decrease. So maybe they are still close to the result at room temperature, but at lower temperature we can see that the ionic conductivity decreased more significantly, and thereby when we assemble the battery, the zinc manganese dioxide battery, the cycling performance is much poorer than room temperature, and the capacity is much lower than room temperature. So this is the problem, and this will still impede the further applications for the organic additives on the application of the aqueous battery anti-freezing. So thereby, we need to find a new method to solve the anti-freezing performance of the battery, and usually we still need to use the hydrogels. So we can see that also for the hydrogels, we can also use the organic additives. However, the organic additives, as we mentioned before, they have low ionic conductivities. For other methods, such as the high concentrated salts, the issue is they have the salt precipitation, the poor electrolyte availability, and when they are used in the hydrogels, they will damage the mechanical strength of the hydrogels. And another effective strategy is graft the polymer chains. So Professor Zhi has already done a lot of excellent work on this field. But for some of the literature, the method is relatively complex and may not be suitable for the future commercial application. So here we still need to find a more facile strategy to get the high performance anti-freezing and hydrogel electrolyte. So recently, as we all know, Professor He has published several excellent papers on the Hofmeister effect. She has already published papers on nature and advanced materials. And for the Hofmeister effect, we can see that the left side is the cosmotropes, and the right side is chelotropes. For the cosmotropes, they can enhance the mechanical stability, the mechanical strength of the polymers. And for the chelotropes, they will improve the polymer flexibility. And in addition, for the chelotropes, they can also form the weak hydrobonding with water and with polymer chains. So in spite about this result, we think about that maybe these chelotropes can effectively weak the hydrobonding between water molecules and render the polymer chain with excellent flexibility for the future flexible battery applications. So we chose the we choose the pleiotropic ions, choose the perchlorate as an example, and we choose the zinc perchlorate as electrolyte salt, and to check that with the low concentration zinc perchlorate can we get a hydrogel with the excellent mechanical flexibility and excellent anti-freezing performance. So we employed the polysaccharide, which is more sensitive to the Hofmeister effect, and we polymerized the acrylamide on the polysaccharide. So and we soaked them in the zinc perchlorate to get the hydrogels. And first we check the mechanical properties, and we the result is similar as Professor Hurst's result, and as we can see that with the pleiotropic zinc salt, the elongation of the hydrogel is improved and the stress decreased, which means that the pleiotropic zinc salt can dissociate the hydrobonding in polymer chains and form the weak hydrobonding with polymers. And for the in contrast, for the cosmotropic zinc salt, we can see that the elongation decreased and the stress increased. Means the hydrobonding is enhanced by this kind of polymers, this kind of salt. So further, we check the molecular interactions between water moleculars. So from the IMI result, we can see that with the cosmotropic ionized, the peak shift to lower field, which means that the hydrobonding between water moleculars is enhanced. But for the pleiotropic ionized, we can see that all the peaks shift to higher field, and the hydrobonding between water moleculars is decreased. With the concentration of the zinc perchlorate increased, we can see that all the hydrobonding between water moleculars is further decreased, which means that the pleiotropic ions can form this weak hydrobonding with water. So and also we also check the result with the FTIR. As shown, we can see that a new peak at around 3583 per centimeter formed, and this means that the hydrobonding between water moleculars is further weakened, and the anti-freezing performance should be enhanced by this kind of the pleiotropic perchlorate ions. Based on the above several slides, we can get the conclusion that the perchlorate ions can form a ternary hydrobonding with polymer chains and water. Thereby, the water retention of the hydrogel can be improved, and the ionic conductivity of the hydrogel can be enhanced. Also, we can see that with this, the low concentration, even at the low concentration of the 2 mol per liter for the zinc perchlorate, we can see that they can still provide a high ionic conductivity for about 7.8 millisiemens per centimeter at the minus 30 degrees centigrade, which is similar as the ionic conductivity of zinc sulfate at room temperature. In addition, we also check the mechanical flexibility of the hydrogel at minus 30 degrees centigrade, and they can provide the lower storage modulus and loss modulus and high elongation for at least 320% at minus 30 degrees centigrade. Furthermore, moreover, with the ternary hydrogen bonding, with the ternary hydrobonding between among the perchlorate polymer chains and water, the amount of free water in the hydrogel is significantly decreased. Thereby, the side reactions can be inhibited, and they can provide stable dendrite-free performance both at room temperature and low temperature and minus 30 degrees centigrade. Thereby for the full battery performance, we also check the zinc PNI cell, and we can see that both the battery can provide the ultra stable cycling both at room temperature and minus 30 degrees centigrade, and the high current density, about 5 amp per gram, they can provide a high specific capacity about 80 milliamp hour per gram, which is similar at low temperature. So we further demonstrate that our hydrogel has excellent anti-freezing performance. Last, also for the flexible battery application, we also assembled this kind of the flexible devices and checked their anti-freezing performance and find that they can still cycling stable and they can power this device even after 1 month stored at the low temperature, and they can provide a stable capacity and different bending angles. So for this part, we provide this forming the ternary hydrobonding to decrease to break the strong hydrobonding between water molecules and to break the hydrobonding between water molecules with polymer and between polymer. So as a result, we get a hydrogel electrolyte with high flexibility and great anti-freezing performance. Further, we also checked this molecular interaction regulation strategy in polymer binder in lithium sulfur batteries. And as we know, Professor Zijian Zheng is one of the biggest experts in this field. For the lithium sulfur batteries, the most serious issue is the shuttle effect of the lithium polysulfide. So this for the lithium polysulfide, they will cause the immutable capacity fading, sluggish kinetics, and the self-discharge behavior. So there are a lot of strategies to solve this shuttle effect issue. But so far, the polymer binder is regarded as one of the effective methods because they will introduce no extra inactive materials for the battery. For the polymer binder, they will inhibit the shuttle effect by the functional groups on the polymer chains, but somehow the interaction between functional groups may weaken the inhibition between functional groups and the lithium polysulfide. So here we employed the two typical monomers for the VIPS, what we have used before. They have the much strong electrostatic interactions between the monomers, and another monomer is NAG. They have a very strong hydrobonding between the monomers. So we co-polymerized them together and use the FTIR to find that the interactions, the electrostatic interactions between the VIPS and the hydrobonding between NAG are both weakened by the copolymerization, and the new peak at about 1689 formed for the weak hydrobonding and ion dipole interactions. So as a result, after weak interactions between functional groups, we use DFT to prove that with the copolymerization, they have a much higher bonding energy with lithium polysulfide, and for this binder, the adsorption performance for the binder is much higher than other binders, Thereby we use the in situ Raman to further monitor the performance of the binder. We can find that at around 475, no peak can be found for the PNAVS binder for the molecular interaction regulated binder. But for the other binders, we can see that the above peak for the lithium polysulfide can be observed because to prove that after molecular interaction regulation, the binder can effectively absorb the lithium polysulfide and inhibit the shuttle effect. So, also, due to the great absorption performance, the electron and ion transport route can be shortened, thereby the redox reaction kinetics can be further enhanced. Also, the ion diffusion coefficient can also be optimized in the molecular interaction regulated binder. So as a result, we check the electrochemical performance for the battery. We can see that they can provide ultra-stable open circuit voltages for more than 3,000 hours. Which will be facilitating to the future battery storage and transport. In addition, we also check that this binder can also inhibit the dendrites, the lithium dendrites, and also they can provide very high cyclic stability and rate performance and the high current density of 1C. Since we regulate the molecular interactions in the binder, so we also check the high sulfur loading performance of the battery. We can see that as the ultra high sulfur loading for 11.7 milligram per square centimeter, they can still provide a high area capacity for more than 12 milliamp hour per square centimeter, which has already surpassed for most current reported literatures. And for the practical application evaluation, we also assembled the prototype, the pump cells, and find that they can cyclic stable and different binding angle, and they can provide a stable specific capacity and higher current density 1C, which is similar to the button cells result. So for this one, we check the molecular interactions in polymer band summary. So in this topic, we applied the molecular interaction regulation strategy on the dendrite inhibition performance to guide the zinc deposition crystal length to 002 and to form a weak hydrobonding between water and the polymer to enhance the anti-freezing performance and also to inhibit the shuttle effect to accelerate the lithium polysulfide redox kinetics. So Professor He had already introduced me, so this is my personal profile. And again, thanks to EcoMat and Professor He to arrange this webinar to give us the chance to introduce our result. Thank you.
All right, thank you very much, Professor Jiao. And since we already received a lot of questions, but we wanted to save them for the final roundtable discussion. So yeah, for our audience, please feel free to keep posting your questions on the forum. We receive all of them. We're going to save them for the end to discuss with Professor Jiao and Professor Zhi together. All right, okay, so now thanks, Professor Jiao again. And then now let me briefly introduce Professor Chunyi Zhi. Okay, Professor Chunyi Zhi obtained a bachelor degree in physics from Shandong University and PhD degree in condensed matter physics from the Institute of Physics, Chinese Academy of Science. After 2 years of postdoc at the National Institute for Materials Science in Japan, he was promoted to be the ICYS researcher and senior researcher. And Dr. Zhi is now professor in MSc in CTU. So So Dr. Zhi has extensive experience in flexible energy storage, aqueous electrolyte batteries, and zinc-ion batteries. He has published more than 400 papers with the H index of 108 and the citation over 40,000. He has been granted more than 80 patents. So Professor Zhi is a recipient of Outstanding Research Award and President Award of CTU, and ML Research Award, Beijing Science and Technology Award, first class. He's the Caribate Analytic Global highly cited researcher in 2019 to 2021 in material science sector, and RSC fellow and member of the Hong Kong Young Academy of Science. So with a lot of great awards. All right, so without further ado, so we are looking forward to hearing the presentation on the topic of stable zinc anode of zinc batteries from Professor Zhi. Yeah, please welcome.
Sorry, give me a minute to share my PowerPoint. So it's quite strange. I cannot share my PowerPoint. Give me a minute.
Please take your time.
Give me a minute. Give me a minute. I think I can.
No worries. Yeah, maybe.
I'm familiar with this system, but when I it's okay right now.
Oh, it's coming.
So you can see my PowerPoint in
Perfectly. Yes.
Okay, good. Nice. Okay. So I've been present this topic for many times actually, but this time will be different because first of all, I would like to thank my friend Zijian to invite me for this seminar. Because EcoMat, I remember I published 2 papers on EcoMat on invitation by the chief editor. After that, actually, now I'm working on another journal. I also talked to Zijian for experience sharing, and he taught me a lot how to advertise for a journal. Well, we've been friends for many years. Okay, let's go back to the today's topic. So I would like to talk about the zinc anode. Because as for the zinc batteries, I remember it's been starting to be a hot research topic probably in 2004 to 2005 around. Then from 2018, yeah, only 4 years ago, that people start to focus on zinc anode. But before that, okay, let's start from 2014, 2015 around. Then from 2018, that people start to work on zinc anode. That previously people focus on more on like cathode side with different materials to pursue for the high capacity voltage operation and so on. But after 2018, there's a lot of research on zinc anode. Well, that was not that long story, only 4 years, but with the huge background of the lithium batteries, a lot of research on lithium anode, that the progress on zinc anode is going pretty fast actually. There's tons of research with similar strategy with lithium-ion batteries, and a lot of even 2 or 3 years ago that we can only achieve probably only 2 milliampere per centimeter square. Now we can achieve even 20 milliampere per centimeter square. That seems a big progress, but it's time to think in details in this field. That's probably today's topic. So I would like to still start from the lithium-ion batteries, as we always cannot avoid, because in terms of performance, in terms of the commercialization progress, these zinc-ion batteries much behind the lithium batteries. So the current major projects, energy storage in this world, is basically about lithium batteries, target on energy storage, target on the energy density, specific energy, and so on. And we're also using more and more lithium batteries, but we are also having more and more problems, accidents, even sometimes we can call it disasters. We use it for EVs. We do not have choice, because for EVs, even we use the best lithium batteries, we still have the anxious about the lifetime. The other one is we are now using for energy storage devices, energy storage systems. We are building up larger and larger systems. Then okay, we're having more and more like disaster level accidents. So if you analyze the application scenario of batteries, that lithium battery has been this big success, giant success, because of the applications of them in the field of EVs, electrical vehicles, and mobile phones. There's two typical application scenarios for lithium batteries, because these two applications, they rely on the energy density very much, because these batteries, they are running on the road every day. So you need a smaller, lighter batteries. But for other application scenarios, for household energy storage, for large-scale energy storage, in combined with the renewable energy systems, that you probably you do need energy density again, but it's not that primarily important, because many batteries will stack up in one place. You may have the problem if one battery got to catch a fire, that you have some runaway. That can be very dangerous. So another issue for some very portable devices is they do need energy density, but on the other hand, they also need safety, because they are portable. We use it at home, that we have this kind of problems. If you compare lithium batteries with zinc-ion batteries, or let's say zinc batteries, okay, a slight difference between zinc batteries like zinc-ion batteries. They generally work at different magnitudes. But if you look through all these material systems, that for lithium batteries is a very typical system that target on high energy density, that use very reactive materials and dangerous materials, pack them together. That's built up the very compact high energy system, but on the other hand, it will also drag down their safety performance. On the other hand, if you go for zinc-ion batteries, that's much safer than lithium batteries, because you think about zinc metal, it's not as active as lithium, and also metal oxide is stable. And you put all of this in a tank of, say, water. So that makes the system very safe. But on the other hand, because our water is highly corrosive, if you put salt in, that's even more corrosive. So this kind of system, stability, energy performance expression is much behind our lithium batteries. In particular, in recent years, the lithium batteries achieve very high energy density already. But okay, nowadays we have large-scale energy storage systems. That's probably a chance for zinc batteries, according to just our observation. If you take the weapon of safety for zinc, you could have a chance, to have a corner or have an area in the large field of energy storage. But only when you solve the problem of unsatisfied energy performance. Nowadays, although we do say that probably for zinc-ion batteries, we do not have to emphasize energy density, because for large-scale systems, you do not need much for energy density. But the other issue is if you only have very low energy density, that will make you not compatible in terms of the price, because your energy density is low. That means you use the same amount of materials. Even your materials can be cheaper than lithium-ion-based materials, needed materials. That your materials are cheaper, but your energy density is low. So when you divide by energy density, the watt-hour price will be not as low as will be not competitive. That's another issue. So that means energy density is not a primary concern, but still you do need it. Otherwise, you cannot control the cost. Okay, back to the dendrites issue. Dendrites is not a new concept. Sometimes we do feel that for zinc batteries, dendrites is not dendrites. The dendrites is a concept that we take from the lithium batteries. In that case, for lithium, it's more like a dendrites, but for zinc, it's not that much like a dendrites. It's just some roughness or some platelet growth or so on. But before that, actually, we identify that the dendrites, they have dendrites or not. We don't know exactly. Even nowadays, actually, for zinc, we do believe zinc has dendrites. So you have to solve this problem, otherwise your battery cannot work stably. But on the other hand, if you go for manganese, it's quite interesting. Many reports, they claim that manganese, there are no dendrites. But in recent years, days, somebody also observed the dendrites for manganese and also for iron batteries as well. Somebody also claimed there's no dendrites for iron, but still in recent days, I remember there's some reports for dendrites. I think dendrites is like deposition. It's not uniform. Well, originally you have a piece of metal, while the surface is not 100% not 100% smooth. Then you have some something like roughness that will generate on uniformity of the electrical field. And this field will be exhausted. Exactly the deposition, uniformity of the deposition that will cross the very rough surface. So that's generally for any metals. Of course, when you have different thermodynamic and kinetic issues involved for different metals, you can have different, say, different ability to inhibit the dendrite growth, but they do all have this. Previously, we have zinc manganese oxide batteries, but it's based on alkali solutions. But nowadays, we change this to multi-electrolyte. A lot of research based on so-called multi-electrolyte research, but I have to emphasize and also have to remind the community that multi-electrolyte is not an advanced technology. It's been studied for many, many years, even before the alkaline technology. But years ago, that's when the battery is trying to be commercialized, it turns out the alkaline electrolyte batteries has even better performance. That's why alkaline batteries was commercialized first. And multi-electrolyte, which was not new, but although nowadays we do a lot of new research based on this multi-electrolyte. Okay, when we switch from alkaline to dendrite to multi-electrolyte, we do have some advantages, like even without any treatment to the zinc metal anode, you use a piece of zinc, you can have, well, let's say not excellent but decent stability evolution that you can have like 1,000 times cycles. That is possible. In that time, I was surprised that probably there's no dendrite issue, but it turns out if we study in detail, so we found that with different current density, say here, if you have small current density, well, you can last for over 100 hours, but if you have large energy density, current density, that it can be much shorter. And if you have you have different capacity, for example, from 0.1 to 0.2, although they have the same current density, that the size can be much larger. The capacity in the symmetrical batteries is corresponding to the loading mass or cathode. That is, that when you have very small size battery with very little amount of cathode materials loading mass, that you can have a very stable battery. But that kind of battery, they do not have any energy density. That if you want to increase energy density, you have to increase the loading mass of cathode side. Then you will have the stability issues. So if you have this problem, you can develop many approaches to solve this problem. Coating is one of them. Coating is not new. Coating is been used for lithium batteries so many times. So we used, for example, this graphene. New materials, they have some porous structures. That we also find that zinc can catalyze the growth of this material. Previously, people used copper. Then we use zinc that can catalyze. So you can grow this graphene uniformly on the surface of zinc, and it can protect your zinc anode. Although the current density was not that large, then you can change it to other materials, for example, zinc fluorides. A thin layer of zinc fluorides, it's claimed zinc fluorides have some conductivity for fluorine, for zinc ions. Although now actually we are trying to confirm that. We noticed some interesting phenomena with this kind of thin film that it can protect your zinc anode, and also it can inhibit the hydrogen evolution, because zinc fluoride is insulating to electrons but conductive to zinc ions. It can separate your zinc anode with electrolyte, no electron contact, so you don't have the evolution. We're also trying to build up something called like graphene dye, not graphene dye, gradient fluoride alloy, that from outermost to the inner parts, they have different composition to solve the problem that if you use insulating materials, you will affect the kinetics. If you use conductive materials, you do have the hydrogen evolution. So if you have this gradient, that coating, that you can inhibit the hydrogen evolution, and you can also have the uniform deposition. So that's a kind of a combination of two types of coating materials. So following this way, that you can use a lot of different technology to solve the problems. For example, you can monitor pH value variation. You can use organic anode. You can use solid state electrolyte. You can use SEI coating. That we have some papers on publication, but I would like to emphasize there's something I've been thinking for a pretty long time, but I haven't figured out which one is eventually will win. For example, zinc foil or zinc powder. Zinc foil, nowadays, that when we do experiments, you take a piece of zinc foil and use it as an anode. It's quite easy to operate, right? Quite easy to operate. I believe 95% of zinc batteries reported in the literature, they use zinc foil because, I'm not quite sure it's because people always do believe that zinc foil is the future, or it's just for easy operation, because zinc foil, it will be much easier to use to operate. If you have powder, you have to make a paste, your coating, that's much more difficult to operate. A lot of more procedures. But if you think of this too, that's if you think about the cost, adjustability, current collector, active material structures, that's typically for many high power devices, additives, conductivities, for example. If you only use zinc foil at low zinc utilization, that will be fine, because you still have a lot of zinc to work as a current collector. But if you go for high utilization of zinc, for example, you have 50 micrometers, you take 40 micrometers zinc away, then you have only 10. Other structures not integrated. So the conductivity will become worse than the whole, without the conductivity, the battery cannot work properly. And okay, if you use zinc powder, you have the problem of gas evolution. For example, P4 powder, you coat it on copper, that you see even without any cycling, you still have very intense hydrogen evolution. If you look at the picture, that even without any operation, you put the zinc powder on copper, that you will have bubbles come out and the zinc will be dissolved. Why? Because zinc and copper, it is a primary battery, right? Zinc and copper, they have different potential, and you put it in the electrolytes. So you have two electrodes and the electrolytes. This is a battery already. This is a primary battery. Then zinc will start to be dissolved. And if you look into this, that you will see that the freedom model is totally different. That with zinc foil, you have short circuit, and for zinc powder, of course, you will still have the short circuit, but before the short circuit, that you have polarization. That is because of the particles. That after the growing, the redeposition, the surface of the particles become rougher, and they start to separate from each other. Will gives you large internal resistance. Will generate the polarization. Okay, if you use tin to coat copper to solve the problem, to partially solve the problem of the primary battery, that you still have the evolution, but on the other hand, it's greatly inhibited. And the storage life is getting better, and also you see the battery performance. This is without a coating, without tin coating. There's with tin coating, that you have the stability is much more improved in terms of storage stability, although it's not 100% soft. Okay, that's our concern in terms of the stability. Then we go for another one. Is previously we studied for we did a lot of research on flexible batteries. I'm thinking that for I was thinking that for the flexible devices, because if you have bending or folding, that at the corner, that you have the concentration of the electric field, so the dendrite issue may be enlarged. You can see the dendrite even easier. That's correct. When we did the research, for example, even you have a battery at a planet test, you can last for 100 hours. When you fold it, that you only have 40 hours. If you study the dendrite's growth or some roughness, that from far to the folding area, so the size of the dendrite is getting larger and larger. And also it has R dependence. R, it means, if you fold it, it's a very small R that will give you the even shorter lifetime. And then we're trying to solve this problem, because we're trying to solve this problem. Previously, we think about what insert electrolyte, because well, it seems that there's not that much we can do, because it's intrinsically problem for the flexible devices. That if you deform, that you have enhanced electric field, that will generate uniformity. Okay, so then we solve this problem. We're trying to use water insert electrolyte, but turns out still we see the dependence between although the surface become sort of not that rough anymore, but still we observe the dependence between R and the lifetime. That means water insert electrolyte cannot solve this problem. So we analyze the problem for the dendrite's growth. First of all, it's because of the electric field strength, right? Electric field strength, if you approach zero, here, the electric field will be remarkably enhanced. That's one issue. The other one, this one actually we cannot solve. Nobody can solve this problem. It's an intrinsic issue. The other one is if you use the gel electrolyte that's contact with the electrode, when you're trying to bend this detachment between the gel electrolyte and the zinc and the electrode. So this one will also generate uniformity. So we trying to develop a kind of hydrogel which based on highly concentrated salt electrolyte. That one has very strong in terms of the in terms of the mechanical strength, it's quite strong, and also it's very adhesive to any surface zinc foils. After bending, after cycling, you see the very good interface. So we noted that the dependence between R and the cycling time is almost, we cannot see it, although the polarization will be different. But honestly speaking, this is not 100%. We did not 100% solve the problem for the flexible devices because we cannot solve these problems. We use a very strong hydrogel to block the zinc dendrite growth. That's what we have done. That can partially solve the problem, but cannot 100% solve it. Okay, I remember I have 2 minutes more. Okay, another issue is in recent days that we noted that because when lithium batteries will be different from zinc batteries, because zinc batteries, when you fabricate zinc manganese oxide, zinc vanadium oxide batteries, for these batteries, you do not need to charge, you directly discharge. So when you discharge, zinc is being stripped. Will be stripped. So we did a systematic, detailed study on the stripping process of zinc. For example, a uniform, smooth zinc surface after stripping, that we identify a few steps for stripping. You can see that, for example, stripping of active zinc or stripping of some bulk zinc, that they exhibit different shapes here. And when you do the stripping, that first you create pits on the surface. When you do stripping, generally it's getting rougher. Then with this rough surface, the evolution of the morphology, that after a couple of stripping plating process, the surface getting much rougher with porous zinc accumulated. But when you go for plating, that's first you do not stripping, you depreciate the zinc. Then there's also a few steps then, but you see the difference that the surface after the first depreciation that can become much uniform. And we also develop a method that's the morphology evolution, that from stripping, from plating, that after a few times stripping, that even the third plating, you see the surface is getting much rougher than the surface being initially plated. So this is the evolution that is starting from the pristine, the cycled stripping zinc is much rougher than the cycled pre-deprecated zinc. So we also use this technology to, if you pre-depreciate some zinc on the surface, that's the stability of the zinc evolution will be much better. So this is one of the observations. The other one is very interesting. In recent 2 years, I remember there's a lot of reported very large numbers in terms of the current density. As I mentioned in the beginning, that the current density is a challenge, and area loading mass is another challenge. If you go for current density, that we calculate the accumulated capacity here, and this is current density, that you will see for the circles, this is for symmetrical batteries, that accumulated density and energy densities and the current density is very large. You can easily get the 10,000 times of accumulated capacity, and the current density from 10 to even 80. That's insane. And for some stars, this is non-symmetric batteries. Well, the contrast is very large. That means if the symmetrical battery is used to evaluate the reversibility of zinc, the reversibility exhibited in the symmetrical batteries should be the same with the reversibility of in the non-symmetrical batteries, but you see the large diversified state presentation. If you go for overpotential, also very diversified that you can collect even from 80 to from 90 to very small numbers. So if you study in details, you will find it very interesting that for some batteries, they exhibit a very good cycling stability. Symmetrical batteries, if you can get this kind of curve. Widely reported this kind of a curve, but if you measure their impedance, that you will find that the resistance is getting much smaller. It seems that from here to here something changed. But if you only read this diagram, this chart, it's almost the same with this normal batteries. Then we analyze the battery status. That can be normal, can be short circuit, can be soft shots. The normal one, there's no short circuits. The normal one is in between. You have electrolyte, the ions being transferred. Then you have capacitance and resistance. You have a normal. You have a normal resistance here, and you also have generally this kind of shape of stripping plating. But if it's a short circuit, that you only have resistance left, and the resistance can be very small, and you do not have this one. So this one is easy to identify. But between these two, you do have soft shots. That means it's partially shorts, and you still have capacitance, but you have one more resistance added here, and the resistance number is much smaller than the normal status, but you still have this kind of charge-discharge curve. It seems it can be still charge-discharge, but the battery has been short-circuited. Okay, so we recommend when you test that you during the cycling test, you need to measure the impedance. That if you notice the resistance is not that large a change. Here we change the current density. Although you see that some change of the resistance, but if it's not that large, we believe the battery is unstable. But of course, it's not that largely changed. But how large is large? Nobody knows. But then, if you do the temperature variation test, you go for please remember that always go for low temperatures, for example, -10 and -10. And if it's normal batteries, you can get this kind of curve. But if it's abnormal batteries, you can get this kind of curve. If you calculate activation energy, one is a normal cell is positive, but for soft short cells, it can be negative. Okay, so that's just recommended test protocols you have to evaluate. I'm sorry, this is in Chinese. I can briefly translate. So in the field, actually, I do feel we have achieved a big progress, especially in terms of the numbers. We're getting larger and larger numbers. Although we feel these numbers they have some problems, although they do not reflect the normal and the batteries, the large size batteries which can be eventually used. Almost all the large numbers are achieved in the very unpractical conditions with a large amount of electrolyte and a very large NP ratio sometimes, and the utilization ratio of zinc is very small. So zinc anode, if you do initial stripping or initial plating, that matters. That will affect the evolution of morphology in the following cycles, very large. And also, when you do the measurement for symmetrical batteries, trying your best to avoid soft shots. When you have a super stable batteries, you have to be very careful with the soft shots issue. Okay, that's my acknowledgement. My time is almost over. Okay, I would like to thank you for your attention, and thank the organizers to invite me. Thank you.
All right, thank you so much, Chun. And now we have collected quite a few questions. Since Chun, you just presented, why don't we just quickly start from questions from you, and then we pass on to questions to Professor Jiao, and then we will have a discussion together. Does that sound good to you?
Sure. Yeah. Should I still share my PowerPoint or just?
It depends. So let me just read the first question to you. Okay. Yeah. So, how do we increase the voltage of zinc electricity? That's the first question.
Well, yeah. We've been struggling for battery voltage for pretty long time. That for high voltage, you have to optimize electrolytes and also electrode. The problem is even you have the electrolyte with the wider electrostability window, but you do still have the problem that the potential high potential materials is generally not that available. Actually, if you count that, if for example zinc is minus 0.276, if you want to have a 2 watts, that you need a very high potential cathode materials. That's not easy to fabricate, honestly speaking. I don't see a lot of candidates, and we do have some candidates. We can take some from the lithium batteries, but they have the stability issues when you use it for zinc batteries, because without, for example, you take a lithium ion materials, you use it directly as cathode. Without the support of lithium batteries, zinc will intercalate it. Then after the first intercalation, that zinc cannot be get out, cannot be deintercalated. So the battery will generate that. You can use a hybrid strategy to try to improve the stability. But I would like to remind for high voltage batteries, for research, for publications, because performance is performance, 2 watts is higher than 1.5 watts. And also, if you go for high watts, you can easily increase energy density. But the point is, we have to respect zinc batteries. Generally, we consider it as a kind of aqueous electrolyte batteries if we stick on this. And I noticed some professors in the community, they trying to avoid aqueous electrolyte. They trying to go for organic electrolyte. Okay, that's part by part. Let's go for aqueous electrolyte. We have to respect zinc ion batteries as aqueous electrolyte batteries. In that case, we should not pursue the high voltage that much, because high voltage in the aqueous electrolyte batteries always cause troubles. So if you want the device to be useful, you have to go for balance, the balance between the voltage, your cycling stability, and your capacity, and so on. If you try and struggle for high voltage, you do have the problem. You will sacrifice some other performance. But of course, for publication, for research, you can always try to achieve high voltages. Another way, if you go for organic electrolytes, well, that can partially solve the aqueous electrolyte issues, that you do not have to worry about electrochemical stability. But the problem is, if you make zinc ion batteries be organic, how do you compare with lithium batteries? That could be an issue, because we sometimes claim zinc ion batteries is fundamentally safe because of the aqueous electrolytes. If you go for organic, then you have to choose the organic one, but the safe electrolytes. Otherwise, it will lose. If you compare with lithium batteries, you will lose the capability to compare. Actually, that's my general comments. That's a big issue. Yeah.
Okay. Thank you very much for sharing with us your thoughts of how to increase the voltage of zinc electricity, and also the insight about appreciation of the safety of the aqueous system, right, of the zinc ion battery. Okay, very good. And then quickly, next question: how to prepare the zinc slide sample for SEM?
Zinc slide sample. What does it mean, zinc slide?
So basically, how to prepare the sample for the SEM? How to slide prepare the SEM imaging sample.
Yeah, I don't feel this is a problem. If you're talking about zinc anode, you're just disassembling the batteries. You take the zinc from the battery to use. I do not understand this question. I'm sorry.
Yeah, it's just a direct disassembly, and then you can directly view this interface. Yeah.
Well, yeah, that depends. Okay, that's another issue. That depends. That's okay, because if you use aqueous electrolyte, you can easily deassemble the batteries. But sometimes you use, for example, the highly adhesive electrolyte. That it can be hydrogel, for example. Some hydrogels highly adhesive. That when you're trying to deassembling, that will destroy of your zinc morphology. That could be an issue. That could be an issue. Is that one that I don't have good suggestions? That's first of all, when you do this, that you can tell people that when I do assembling, deassembling, that my electrolyte is quite adhesive. The morphology, I report it might be not the real case because the hydrogel will destroy the morphology. You can tell. You can always tell. No experiments are 100% precise. You can tell your audience, your readers about this. Another way is probably if you immerse it in water for a pretty long time, that can detach your hydrogel from the zinc anode surface. That can possibly solve this problem. Not 100%. That's my personal suggestion. Thank you.
Okay, great, thanks. And then another question is regarding the soft short circuit and short circuit. Then so basically what's the difference and also what's the cost for the soft short circuit? And is a soft short circuit considered as a death of the battery?
Not really. Actually, quite interesting that soft shorts is for symmetrical batteries. If you go for 4 batteries, if you have soft shorts, that's generally this 4 battery cannot be properly used. If you have soft shorts in 4 batteries, the 4 battery cannot be properly used. I'm talking about the soft shorts in symmetrical batteries. That one, that it looks is still okay, and you can collect data. And also, if you don't look into details, the data looks normal. That's a problem. That also gives you that's why in a full battery you cannot achieve very good cycling stability. That's when we do the full battery test, probably only with zinc manganese oxide probably only 1,000 times cycles, and even with the zinc carbon usually 10,000 cycles. But if you calculate the accumulated capacity on the zinc anode and you compare with the symmetrical batteries, you will see that symmetrical batteries, they have very large number in terms of the accumulated capacity. That's quite interesting. Why this even full battery symmetrical batteries, they all used to evaluate the reversibility of zinc. Of course, for the full battery, you have the anode, the cathode issue, but the cathode generally is, if you use large amount of them, it could be not a problem. So these 2 batteries, all the tests are based on are limited by the zinc reversibility. But why is that in the symmetrical batteries much easier to demonstrate very good numbers in terms of the cycle time and also the current density? Why in the 4 batteries it's much difficult, and we do not even have the data, large size, the high accumulated capacity. So the difference is because symmetrical batteries, you have soft shorts, you can still collect the data, but for 4 batteries that you have soft shorts, you cannot use it anymore. Okay, so when you have a symmetrical battery, you have soft shorts, the battery is still not dead, it's still alive. It looks still good. And interesting that soft shorts, if you go for high temperature, soft shorts is very weak, then it will break. Then this become back to normal batteries. So for symmetrical batteries, sometimes you see that we become soft shorts, then back to normal, then soft shorts again, then back to normal. You can see these kind of cycles. So that's okay. That's my answer. Sorry. Thank you.
Yeah, thank you. And then there's a quick follow-up question: how to determine whether a battery is short-circuited on a symmetric battery voltage capacity curve?
Yeah, you can see a general judgment that's general judgment. You will see that for you can see my screen, right?
Yes.
Here, sorry, here. First of all, if you look into the charge discharge curve, if you have this, that you will notice this is soft shorts. This is soft short circuit. You will stop measurement. But if you have this, you will still continue because it looks normal. You still have up and down, up and down. But actually, you see this one and this one, they are different. If you have this, that you probably you should think about it is soft shorts or not. So, and also I would like to recommend you to stop doing the cycling stability test and then measure the impedance. But generally, usually soft shorts generate from the very starting point of the cycling test. I mean, if you do the cycling test, for example, you can do it 10,000 times, but you do the impedance test probably in the beginning, and 100 cycles, 200 cycles, if it's stable, it will be generally fine. It will be generally fine. The soft shorts generally, when you apply a high current density, and suddenly it starts the soft shorts. And then if it becomes stable, there's no soft shorts, there will be no soft shorts for a long time. At the beginning is a dangerous period. And also, you can evaluate, for example, with low temperature test. Well, that's maybe from the starting point, you see this kind of normal curve, you put it back to the room temperature for test. That's my recommendation. Let's make the test be more complicated. I understand for students that, well, for cycling test, you just fabricate a battery, put it on the on the charge tester, then leave it for a long time. That's the easiest way to. I have this problem as well in my group. I ask all of my students to do this kind of precise test, but some of them, well, they still it's too complicated. Well, that's my observation. Thank you.
Okay, thank you very much for sharing this very valuable advice. All right, due to the time limit, maybe we can just switch to some questions for Professor Jiao, and then we will come back to have a common questions for both speakers. Okay, so Professor Jiao, here are a couple questions for you. Then for the zinc battery, is there a general requirement for the setting for testing the current density? Current density. Yeah.
Sorry. What does that mean? So usually for the zinc symmetric battery, the test step is very common. So what does that mean? Sorry.
I think here the question is the general requirement for the setting, like how to design the test for the current density. Maybe this is a little bit too fundamental, very basic. Maybe we can look at the other question. So in the demonstration on your PPT slide 12, in the demonstration experiment of small and medium-sized light bulbs, how many volts were used to light the light bulbs? Where do you that's where to get the bulb set for this very specific demonstration?
Let me see. So can you see my slides?
Mm-hmm.
Okay, so about this, so we use usually these lights need high voltages, so we assemble we take around three devices together to power the lights. I don't know what this is also very common in the flexible batteries application. So,
sure.
For the voltage for the battery is usually about lower than 1.5 watt. So So for power this kind of lines, so we take them together.
Yeah, for your slide 9, if you go back, yeah. So is sulfide more strongly bound with the zinc ion? Yeah, if the sulfide is strongly bound with the zinc ion, then does it mean when the zinc dissolves, it needs more energy, and the zinc deposition will be slower with this bonding with the sulfide?
Oh yes. Okay, that's a good question. So yes, because of the electrostatic interactions between the sulfonate and zinc ions. So yes, usually due to the high interaction, the transport of the zinc ions usually, for me, I feel that it's much easier, not much it's difficult to deposit, because it will form a transfer bridge to let the zinc ions transport. So I don't know if this question, the answer is okay for the question.
Yeah, I think so. And then similarly for DMSO, would this apply to DMSO as well?
Is DMSO? Okay, I understand. I'm sorry. Okay, so for DMSO, as we can see that. Okay, we can see this from the liner sweep voltmeter and from the cyclic voltmetry test. For the CV test, we can see that the nucleation oven potential is much higher with more DMSO. So thereby the zinc deposition morphology could be more fine-grained, and yes, it's more difficult for the zinc ion to nucleate, to deposit with DMSO.
Okay, I see. Thanks for your answer. And then yeah, so we have about 4 minutes. Then there are some common questions for both speakers. So at present, what are the pressing problems that need to be solved in zinc electricity? Feel free to share your thoughts, any of you. So basically the pressing problems for zinc electricity.
Sorry, this is for general discussion, right?
Yes. Feel free to chime in anytime.
Oh, let me I have a few comments. General problems. Okay, if you look back to the history of zinc batteries, actually, it's pretty old technology. When it was, I remember, it's 1816 around that time that zinc batteries being sort of commercialized. After as the second battery be commercialized after the lead acid battery. So you have zinc battery. By that time, it's generally alkaline system based on zinc manganese oxide. That's primary batteries being used until nowadays. We have dry batteries in the supermarket we can still buy. But okay, the problem for zinc batteries is evolution to the secondary batteries being continue to, for example, last century. That's 1918s and 1990s. Around that time, we already achieved a very good stability. If you look back to the old literatures, you will find that a lot of research we're doing now that's actually similar to that research in last century, 1980s, 1970s around. Because if you look into all the materials we're using now, that's also pretty similar. Okay, then after that, the progress on zinc batteries, the research is getting slowed down because I believe it is because of lithium batteries. So because lithium batteries apparently they have much higher energy densities in terms of perform much better than zinc batteries. So then lithium batteries just jump in, that a lot of people were attracted to the field of lithium batteries. Okay, then after that, you know, the progress on zinc batteries is much slower than lithium batteries. Nowadays, we have a big success on the lithium batteries. Why we are we'll switch back to zinc batteries, because okay, I can give you some numbers. Right? Even nowadays, we feel our life is full of lithium batteries. In the battery market, actually, lithium batteries only occupy 50% of the battery market. There's still another 50% occupied by other batteries. And also, one of very senior people, he worked as CTO of GP Batteries, has been retired actually. He said when he joined the battery industry 20 years ago that he was looking for a general battery for all application scenarios, that he'd been trying to struggle for 20 years until the day nowadays he has retired, that he hasn't found any general batteries which can be used for any application scenarios. So that means that for different application scenarios, we need different batteries. I think that's a general judgment that also gives a chance for zinc batteries. So the current problem, I believe, for zinc batteries is that all the current research on zinc batteries, the platform we're using is based on coin batteries. We use very small size batteries with we do not control NP ratio. We do not control the electrolyte amount. That we take a very simple procedure to fabricate the batteries because that's quite easy, and then okay, that's why we can have a tons of data and tons of paper in short time. But the problem is this kind of research, although we have a large number, we can easily collect large numbers and larger and larger. The numbers getting larger and larger. But because the platform itself, it has its shortcomings, it's typically not a practical battery. And the bottom batteries cannot be used. And the battery design is not practical. So all the research data cannot be actually, when you're trying to consider this field, when you're trying to consider this kind of battery seriously, how to use it, that all the research produced data cannot support the next step research. That means even you demonstrate very good cycling stability in the system, in the material system with the coin batteries, when you're trying to make a large size battery, we'll see totally different. That's not like I can achieve like 10,000 times cycling. Then if I switch to large size battery, I can have a discount. For example, I can have 10,000. I can have 1,000. That's only 10% of my original data. It's not like this. That's like you can achieve 10,000 cycles in a small size battery. But if you go for large size batteries, probably you can only have 10 cycles. So that means that's 10,000 times cycles. Cannot be used as a reference for your real battery development. I believe this is the largest problem that all of researchers, including me, and a lot of friends of mine, that we spend too much time on data collecting. We spend a lot of time to achieve the large numbers, but that 10,000 is not useful. Okay, that's my comments. Thank you. Yeah.
Okay, thank you. That's very valuable and very fair insight and opinions. Yeah. A quick question: are there any welding considerations and issues which are common between the electrolyte and anode or cathode? Are any like surface treatment to improve the welding?
Should I answer this question as well, or
any of you? Yeah, please.
Professor Joe, you want to answer? You have a few comments? I think it would be not appropriate for me to take all the questions.
No, you are one of the biggest experts in this part. So yeah, I think.
So basically,
for me, I did, actually for me, I didn't do any wetting treatment on the surface, treatment about on the surface of the thing. So usually I just use the gel electrolyte and do no wetting procedure. But if we use the solid state electrolyte, maybe we need the wetting the surface of the electrode.
Okay, let me add a few points. A few years ago, I feel that since we're working on the aqueous electrolyte batteries, so the hydrophobic, hydrophilic electrode should exhibit different performance. So I asked my student to work on this. I also looked for a kind of a plasma machine to treat the surface of the electrolyte. But that time, at least that two students that didn't collect any useful data. They do not feel any difference. That's quite strange. That's why strange. So if the particles, if the surface of electrolyte is hydrophilic, I suppose it should be better for the high performance, but it turns out they did not observe any difference. Okay, that's one of the observation, but I do believe this is still very meaningful topic to look into the details. So but I failed. And another issue is for if you are waiting that nowadays we are also working on some solid state mentioned by Professor Joe, that the solid state batteries will use polymer. Well, I also tried with the ceramics, but I didn't succeed. I haven't been successful with the ceramic electrolyte. But for polymers, we can make solid state polymer electrolyte. But at that time that we do need wetting. That's generally we immerse this polymer films in the electrolyte, then we take it out and we dry it. And the interesting is we also dry it. But even after this drying, we still at the interface it can be much improved. We do need it. This is quite similar with lithium batteries. Previously, people always claim all solid state lithium batteries, but turns out nowadays they also said they're liquid or solid mixture, mixed use. So that's my comments. I generally believe that if you modify the hydrophobicity or hydrophilicity of these particles and surface of the electrode, that will contribute to the performance enhancement of the batteries. Although I haven't been successful to demonstrate, I do believe this is a good idea to proceed. Thank you.
I see. Yeah, very helpful opinion. Due to the time limit, I don't know. There are still quite some questions, and since this is really well received presentations from both of you, maybe let's end with the very last general question. What's the main scientific problems for gel electrolysis that need to be solved? Maybe in terms of the criteria of the gel electrolyte materials, if that helps.
Yeah, I would like to leave this question to Professor Joe, because you talk about gel electrolyte today.
I'm sorry. So
maybe the main or general scientific problems that you feel like the gel electrolyte need to be solved.
Okay, probably let me start with a few points. That's sure. Because I work on gel electrolyte, hydrogel electrolyte for a few years before. Previously, I used gel electrolyte for flexible devices. At that time, I feel that hydrogel is hydrogel. Hydrogel contains a lot of water. Then in general, in most cases, for the ionic conductivity, that's not a big issue. That in general you can achieve high electrolyte ionic conductivity. But on the other hand, if you use hydrogel, that's you are having a kind of quasi solid state devices. At that time, I did a lot of games, say multifunctional devices. That I feel that with quasi solid electrolyte batteries, you can have multifunctional. But it turns out, honestly speaking, battery is a battery. You make it to be multifunctional, you lose something. Yeah, it gains some function, you lose something. The something you lose, that's unfortunately in most cases, it is the performance of the battery. So that's not acceptable. So you get some functionality, but then you lose the performance of the battery. So I figured out this. I noticed this. Then I switch back to the focus on the battery performance. So my point nowadays, my point is if the gel can contribute, again, battery is a battery. If the gel can contribute to the performance of the battery, no matter it's high voltage, for example, you use a gel to confine water molecules to achieve a wide electrostability window, that you can use this kind of gel to for high voltage. Or like Professor George just demonstrated, if you use a gel to stabilize the zinc anode, or sometimes you can also use a gel as an artificial CEI to stabilize the cathode side and so on. That will be meaningful. That's again, the battery is a battery. Any gel electrolytes that you have to connect. You have to connect it with the battery performance. And if you go for battery performance, the voltage capacity and intensity and cycling stability, and for example, low temperature batteries also works. And also we can use as artificial SEI and so on. So you have few points in terms of the battery performance, and you can use your gel electrolyte to target on these points. You get any progress that will be meaningful. That's my comments. Yeah.
I see. Yeah. So, we have to ensure the first priority of the battery performance while developing, additional functionalities. Yeah.
Exactly.
Professor Jiao, any additional comments?
Actually, for gel electrolytes, for me, so far, though I didn't care, I didn't do more research about this, but the thickness of the electrolyte is also important actually for the ionic conductivity and for the water content and for others. In addition, about the mechanical property, about the gel electrolyte, with more water content, the mechanical property will be decreased, and this maybe also cause problems during the assembly, and maybe also cause the short circuit. Actually, so far for us, as for our results, we will also feel that the elasticity or the plasticity of the property, the mechanical property of this kind of this part is also important, because it will influence the interfacial connection with the gel electrolyte and with the electrode. So in the future, we also need to take more attention on this part.
Okay, so basically those materials' basic properties, if it's very relevant to the process of battery, those need to be taken care as well. Yeah. All right. Okay, thank you so much for staying late. Then we, even though we still have quite some questions, but due to the time limit, we probably have to end here. Then yeah, maybe we hope to find more time or other chance to continue our conversation. Thank you very much again for Professor Jiao and Professor Chen Yizhi to share their very valuable research progress and insight in the field of nanomaterials for energy storage devices. All right, thank you very much for all our audience.
Thank you very much. Yeah, thank you very much to all audience and organizer, Professor He, Professor Zheng, and Professor. Okay, bye-bye.
Thank you.
Bye. Okay, bye.